So we'll start off Unit 1 here talking about the basic unit of chemistry, which is the atom. All right, we're going to talk about structure of the atom, which should hopefully be a review, okay, kind of the parts of the atom, a little bit about the history of the development of the atomic theory, okay, and kind of why we think the atom is the way it is, okay, and stuff like that. So that's what we're working at today, okay. All of my lessons, guys, set up this way. There'll be a lesson title on the first slide, and then there'll be some key points. The key points are the things that I'm definitely going to assess later. Right, on either quizzes or unit exams or whatever. They're the main topic points you need to get out of a particular lesson. So for this one, let's understand how the theories of the structure of the atom were developed. Basically, it's an example of the scientific method. Okay, we thought that this is what the atom looked like until we got information and data that said otherwise, and then we changed our thinking. Okay, and then lastly, learn the parts of the atom and their characteristics. Okay, what are the three parts of the atom? Neutron, electron, proton. Okay, those are our three parts. So we'll go over those, where they are, okay, stuff like that. But that should be a review for you. Okay, so the birth of chemistry was actually not chemistry. Okay, it was something called alchemy. Okay, and kind of developing kind of experimental method and stuff like that. Okay, but we've been using chemistry for a long time without really understanding always what we were doing. Okay, people knew that if they used certain chemical reactions, they could produce certain things. If they put a lot of salt in meat, fungus and bacteria wouldn't grow on it as quickly. Okay, or that they could make leathers, softer and more pliable by applying certain chemicals to them and things like that. So those are all kind of applications of chemistry that we used before we had a true science of chemistry to investigate why these things worked. We used them just because they did work without really understanding why. Okay. The early idea of matter came from the Greeks. Okay. The Greeks believed that all matter was made of 4 elements. And those 4 elements were earth, wind, water, and fire. Okay, and they had like their own kind of rudimentary periodic table, okay, to do with those 4 elements. Okay, and it made sense at the time. For example, steam was some parts water, some parts fire, and some parts air, which made perfect sense. Those are the 3 things you had to combine in order to get it. Okay, you'd take water, put it on top of a fire, and it turned into air. Okay, so it was some parts of all 3. Okay, lava. Okay, I mean, the Greeks were familiar with volcanic eruptions, so they knew lava was some parts fire and some parts earth. Okay, I mean, hey, it was rocks that were on fire. Okay, it made sense. Okay, so they had this kind of very logical idea about what matter was made out of. Okay, unfortunately, they weren't entirely correct on that, but what they had made sense to them. But a Greek thinker came along and said, you know what? I don't think the 4-element system is right. I think that all matter is made of these tiny particles that you can't see. And we're going to call them atomos, which means undividable. Okay, which means you couldn't break them or you couldn't split them. Okay, now, most people in Greece looked at the guy who came up with this idea and went, I think you've been out in the sun too long. Okay, because Greek thinkers, but that was a great job to have in ancient Greece, being a Greek thinker, because you just sit in the Acropolis and people would fan you with big palm leaves and feed you grapes, and you just had to come up with cool ideas. Okay, like it was a pretty sweet gig. And Democritus, that's this guy, okay, came up with this idea that all matter was made of these little atoms. Okay, but people didn't buy that because he wasn't as well respected as guys like Plato. Okay, and people like that who believed in the 4-element theory. So they basically said, that idea is garbage, come up with something else. It wasn't all bad for Democritus. He was right, not that they found out until like 2,000 years later, okay? But also, he came up with something else that was also pretty good. What do you suppose it was? His name was Democritus. Democracy. He's the guy who came up with the idea for democracy. So he had some good ideas, right? So that was good. All right. So yeah, that was where the initial idea of the atom came from, but then it was just forgotten for about 2,000 years. Okay. During that 2,000 years, there was a period of time where a lot of trial and error experimentation to do with chemistry was going on. Okay, kind of during the Dark Ages kind of thing. These people were the alchemists. Okay, Leonardo da Vinci was an alchemist of a type. Okay, and basically their purpose was to find ways to get rich. Okay, like if they could come up with the elixir of life, some drink that you could drink and become immortal and not die, okay, or a way to turn cheap common metals into valuable ones, like turning lead into gold and things like that. That was what they were trying to do. Now, we know that those things at this day and age are impossible. I can't turn lead into gold. Okay, because we understand that they're made of atoms and that lead atoms are considerably different from gold atoms, and there's no way to just turn one into another. Okay? But at that time, they didn't know that, because what they saw was I mixed these two things together, and when I was done, I had something totally different, which means I can turn these two things into something else. They just didn't understand what they were doing at kind of a reaction or atomic level. Okay? They just saw that I could turn that into that. Why can't I turn lead into gold? Okay? There should be a way, and so they spent a lot of time trying to do things like that. Okay? The problem with alchemy was it was all trial and error. And unlike real science, there was like no communication. Okay? Nobody wanted to share their discoveries and information with somebody else for fear that they might discover the way to turn lead into gold before them. Right? And they didn't want that. So in order for science to move forward, you have to communicate your results and have people repeat them and things like that. That wasn't happening during the Age of Alchemy. Okay? That's what this science was called. It wasn't really a science. It was a pseudoscience called alchemy. Okay? So does that mean a lot of stuff wasn't discovered by alchemy? No, they discovered lots of things. Okay, there were probably like 25 different guys who discovered gunpowder. Problem was most of them didn't live long enough to tell anyone about it, because usually discovering gunpowder means you blew yourself up. Okay, but okay, there was all kinds of kind of discoveries like that. Okay, that were made by the alchemists that we kind of use now. All right. After a few hundred years of this age of alchemy, people started realizing that, this just isn't going to work. No one's come up with a way to do it. Maybe we should start sharing results and come up with a more unified way to do things. Okay, and that's where these two guys come in. Okay, Antoine Lavoisier and Roger Bacon are the two guys who essentially transformed alchemy into a real science. But the way they did that was they came up with the scientific method. Okay, rather than just trial and error. Okay, I'm going to mix these two things together today and see what happens. It was, I'm going to investigate a specific problem. I'm going to have a particular hypothesis, and I'm going to test it in a controlled experiment. And then I'm going to analyze my data, come up with a conclusion, revise, and try something different. Okay, so it became a much more methodical type of a method, which is essentially what led it to become a true science. Okay, using the scientific method. Okay. Upon doing that and sharing of data, we started to learn a lot about the behavior of matter, and the behavior of matter is chemistry. Okay. All right, so the structure of matter is that all matter is made of atoms. Okay. Do we really know what an atom looks like? We have a pretty good idea. Okay. Do we really know? Not really. We can't resolve them clearly and see a single one of them. Okay. But we have a pretty good idea from the behavior of matter what they look like. Okay. But we do know that essentially all things are made out of these tiny little particles. So let's say I had a chunk of lead and I started cutting it into smaller and smaller pieces. Okay. All the small pieces still have the same properties. Agreed? Because they're all what? They're all lead. They would have the same melting point, same boiling point, same density, same whatever. Okay, it's all still the same. If I kept cutting that, let's say I had a knife that could actually cut down to the point where I had single atoms. Okay, all those lead atoms would be the same. Okay, or essentially the same. Okay, and they would have all the same properties as a result. Okay, so an atom is the smallest unit of matter that still retains all the properties of that element. If I go any smaller than that, then I alter the atom and I change what I'm working on. Okay, now, fortunately, can I split the atom with a knife? No. Okay, you don't have to worry about causing a nuclear explosion chopping carrots at home. Okay, you're not going to split the atom with a knife. Okay, the sharp edge of your knife is millions of atoms across. Okay, you're not going, they're that small, right? So you're not going to split the atom with a knife. Okay, it's a very delicate, intricate process involved in doing that, right? So an atom, okay, this part here that's in boldface print, okay, is the smallest particle of an element that still retains all those properties. Okay? That is, it would have a certain number of protons, certain number of neutrons, certain number of electrons. Okay, so in the 1700s, a guy named John Dalton was doing a lot of experimentation with matter, okay, chemical reactions and things of that nature. What he saw in these chemical reactions led him to believe the same thing, the same idea that Democritus had developed 2,000 years before, okay, that matter is made of these tiny particles that can move around. Because what he observed in chemical reactions was that if he started with certain materials, at the end of his reaction, he still had the same materials. They might have been, changed around a little bit, joined with different partners, but he still had the same stuff. Okay, so as an example, if I look at a chemical reaction like, let's say this one. Okay, in this chemical reaction, how many different elements are there? There's sodium, chlorine, magnesium, and iodine. Do I have the same 4 elements on that side? Yeah, okay. A chemical reaction doesn't change the elements that I start with. Okay, that was kind of the death of alchemy. Okay, realizing that by a reaction I can't change lead into gold. Okay, I can change sodium chloride and magnesium iodide into sodium iodide and magnesium chloride, but I still have the same elements that I started with. Okay, everyone kind of follow there? So what Dalton had realized was he never really changed the basis of what he had when he was doing chemistry. He always still had the same stuff, maybe joined differently, okay, but still the same basic materials, right? And that's what led him to come up with the atomic theory. Okay? And the atomic theory is these 4 points. How important do you suppose those 4 points are going to be? Since they form the basis of the science of chemistry. Pretty important. Like first quiz would definitely have those 4 points on it. Okay, so the points of the atomic theory are, first off, Democritus' idea. All elements are composed of tiny, indivisible particles known as atoms. Okay, and that's indivisible, not invisible. Okay, just because they're so small we can't see them doesn't mean they're actually invisible. Okay, indivisible means they can't be broken down. All right, second point. Atoms of the same element are identical, and atoms of any one element are different from those of any other. So if I'm looking at, let's say, an atom of lithium, okay, an atom of lithium has 3 protons, 4 neutrons, and it has 3 electrons. Every atom of lithium looks like that. Okay? All atoms of lithium have the same number of protons, the same number of electrons. They don't always have the same number of neutrons, but we'll talk about that later. Okay? But they all have the same number of protons, the same number of electrons. Okay? Which is why all lithium behaves the same. Okay? But if I look at a different element, like let's say we look at carbon, okay? Carbon's different. Carbon has 4 protons. Okay? Sorry, not 4. It has 6 protons. Okay? It has 6 electrons. Right? Its atoms are different. There's more protons and neutrons and electrons in it. So as a result, it behaves differently and it has different properties. Okay? Everybody kind of with me there? Okay? It's the fact that every element has different atoms. That's why every element is different. And it's why oxygen is a gas and sodium is a highly reactive metal. Okay? Their atoms are different. Okay? The third point of the atomic theory talks about what happens in order to get compounds. Okay? In order to get a compound, two or more elements have to combine with each other. Okay? But they only combine with each other in simple whole number ratios. Okay? So if I had hydrogen gas reacting with oxygen gas, it's going to make, that's terrible too, water. Okay? All the numbers there are whole numbers. Okay? There's two H's and one O in water. Okay? It's 2 to 1. That's whole number ratios. I would never write water like this. H1 0.5. Okay? Because what's that saying I have? Half an atom. I can't have half an atom. Okay? Half of an oxygen atom isn't oxygen anymore. Okay? I can't have parts of an atom in a compound. I can only have whole atoms, which is why it's always going to be H2O. That's two H's and one O. Okay? Always simple whole number ratios. Okay? Dalton's fourth point was the one that put the final nail in the coffin for alchemy. Okay? His fourth point explains what happens when chemicals react with each other and explains why I can't turn lead into gold. Okay? Chemical reactions occur when atoms are separated, joined, or rearranged. However, atoms of one element are not changed into atoms of other elements in a chemical reaction. Okay? The only way I could possibly change an atom of one thing into an atom of something else would be in a nuclear reactor. Okay, if I was undergoing nuclear fission where I was splitting an atom, I get different atoms after. Okay, or nuclear fusion, I force atoms together and I create different atoms as a result. Those are the only two processes that can actually change one atom into something else. Okay, so in this reaction here that we just looked at, this is a reaction where two atoms are joined. Okay, I have hydrogen and oxygen, and I'm getting a single compound out of that. Okay, I could have something like this, which is where atoms would be separated. Okay, I start out with a compound, and I end off with two separate elements. So I've pulled those atoms apart. Okay, so they've been separated. Or they could be rearranged. That could be like the one we looked at a minute ago. So we'll write a different one here. Okay. In that reaction, I've rearranged the atoms. I haven't changed what atoms are there. I had hydrogen, oxygen, and sodium and chlorine on one side, and I have the same atoms on the other side. Who they're with is different, but it's still the same atoms. I haven't created anything new. Okay. All right. So my suggestion would be is that you should probably find a way to write these in your own words so they make sense to you. Okay. So that when I ask you what the 4 points of the atomic theory are on a quiz, you're able to do it. Okay. All right. Questions about the 4 points of the atomic theory? Very good with that? Okay. All right. So Dalton came up with this theory, and then the obvious follow-up question to that theory was, okay, that all sounds really reasonable. What do atoms look like? And Dalton didn't have an answer for that because atoms are tiny. He said, I have no idea what they look like. Okay? At this point, we didn't even know about protons, neutrons, and electrons. We just knew atoms were the smallest unit of matter. So Dalton just said, well, you know what? It seems like spheres are kind of a naturally occurring shape. Let's say atoms look like spheres. And everyone's like, all right, sounds fine to me. We can't see them anyway, so let's go with that. Okay? And so was born the solid sphere model of the atom. Okay? And it persisted for a very long time because we didn't have any data that said otherwise. Okay? We just assumed for a very long time that all atoms were spheres. Okay? The spheres were different for every atom somehow, but they were all spheres. Okay? And that was fine until J.J. Thomson came along. J.J. Thomson was doing experiments with chemical reactions that produced electric currents. Okay? And what he found was some reactions would produce a flow of electrons. Okay? I mean, he didn't know necessarily that there was electrons at that time, but he knew that an electric current could be produced by certain types of chemical reactions. He was working with like batteries, developing cells and things like that. Okay? Well, the solid sphere model of the atom didn't explain where the charges that produce electricity were coming from, because a solid sphere doesn't have any parts that can fall off and become electric current. So he said, maybe the solid sphere model isn't right. Maybe it's like a solid sphere, but there's these negative things stuck on the outside of it. And in chemical reactions, sometimes they get shaken loose. And if they get shaken loose, then they can flow through a wire and be an electric current. So since they make electricity, we're going to call them electrons, and they're negatively charged. Okay? So we revised the solid sphere model because it couldn't explain the results of this experiment, so it must not have been right. So he revised it to say, all right, instead of the solid sphere, we're going to call it the plum pudding model, because apparently it looked like pudding with plums in it. I don't know, okay? But that's what we call it. Okay? It was a solid positive mass with a bunch of small negative particles embedded in its surface, loosely embedded because they could fall off in a chemical reaction. Okay? So that was Thomson's. Okay? Thomson's model, okay, was called plum pudding. Okay? And that model persisted for quite a while as well because it did explain the results of those kinds of experiments. Okay? Problem was, as technology was improving, this is turn of the century stuff, right? Okay. Shortly thereafter, we started having this science developed called particle physics, and particle physics is really what allowed us to discover that atoms aren't a solid mass. They're made of other smaller particles, protons and neutrons. Okay. So this model didn't last very long before people said, you know what? It's not a big solid mass. It's actually small masses, some of which are positively charged. Okay. So they said, okay, well, if the negative one is an electron, let's call the positive one a proton. Okay, and people are like, okay, that seems reasonable, let's go with that. But then there was these experiments that kind of said, well, then atoms aren't heavy enough. If they're only made of electrons and protons, all atoms should be a lot lighter than they are. There must be something else in there that's accounting for all the extra mass. Well, it can't have a charge. We've already accounted for positives and negatives, so there must be this neutral particle in there. We'll call it a neutron. Okay, and so a bunch of different models kind of came and went after this point that they were trying to explain the results of all these experiments. Okay, so some people kind of they stayed with the plum pudding, and they said, okay, so there's just solid mass, and then there's positive and negative and neutral parts stuck on it. Okay, and some people said, oh no, it's like there's separate particles, and some of them are moving and some aren't, and so there was no way for anybody to prove any one of them. So there was a lot of discord about what the atom looked like for quite a while. Okay, so we had, then Chadwick came along, and Chadwick discovered that protons weren't the only ones. Chadwick discovered the neutron. Okay, that carries no charge, so there were also those in the nucleus, or in the atom as well. We still didn't have this idea of a nucleus even yet. Okay, it wasn't until this guy came along. Okay, Ernest Rutherford. Okay, Rutherford is extremely important in terms of atomic physics. He performed an experiment that unequivocally proved that an atom has a central dense nucleus surrounded by electrons. Okay? And the way he did this was an experiment that he was using to try and prove something else, which is one of those accidental discoveries, okay, that proved something interesting without really intending to do it. Okay, so what he did is he took an experiment that looked like this. Okay, he took a type of photographic film. Now, you guys are like of the digital camera generation. You probably never used a camera that had film in it. But cameras used to have this stuff called film in it. And if you exposed it to the light, that's how you made a picture. Okay, so X-rays still kind of work that way. So he took this film and he put it around this experiment. And anytime a particle would hit it, it would create a bright spot or expose the film in that spot. Okay, so he had this source of alpha particles, essentially like an X-ray machine, and he was shooting it at this really thin gold foil. Okay, so imagine like tin foil, but made out of gold and really, really thin. Okay, so very fragile stuff. Okay, he figured it was thin enough that it was only a couple of atoms thick. So if he shot these X-rays at it, there was a chance that the X-rays might get through, because his idea was atoms are made up of some empty space. Okay, they have a dense nucleus, and then there's some empty space around them. All right, so he thought that what would happen with this experiment was that some of the alpha particles would get through, but most of them would bounce back. Okay, he had no idea. He was completely surprised by the fact that actually a lot of them went through. Okay, which meant that the nucleus was a lot smaller, okay, than kind of originally hypothesized. Okay, so when his experiment happened, essentially he had some of the particles go right through, and they didn't hit any atoms. Okay, some hit atoms and got deflected back, some got deflected this way. Okay, basically the amount of deflected particles helped him to measure the size of the nucleus. Okay, and from there he was able to determine that, yeah, okay, an atom has a nucleus, it's small, and electrons surround it. And electrons are even smaller than that, so they never deflect particles ever. Okay? So this gold foil experiment, okay, proved that there is a central dense nucleus, but it's very, very small. Okay, everybody follow there. All right, so that's Rutherford. He's super important because he discovered the nucleus. Okay, so that's Rutherford's contribution. Okay, Rutherford discovered the nucleus. Now, after discovering the nucleus, he came up with what the atom looked like. He was actually wrong because he got what the electrons do wrong. He got the nucleus part right, protons and neutrons in there, but he drew the electrons as though they were all the same distance from the nucleus, which we now know they're not. Okay, so this is actually Rutherford's model right here. Okay, it was often referred to as the planetary model, okay, where they were all the same distance away. They just had offsetting orbits. Yep. Okay, so his model didn't last long, but everybody built on the idea of the nucleus. Okay, a little while later, a guy named Niels Bohr came along, and he was studying kind of what electrons do, and he discovered that electrons have different energy levels. So he said, okay, they must orbit the nucleus like planets orbit the sun, which was a logical conclusion because planets orbit the sun because they're attracted to it by gravity. Electrons would orbit the nucleus because electrons are negative and the nucleus is... What's in here? What particles are in here, guys? Positive protons, right? So there would be a similar attraction there, and so that they would orbit because they're attracted to the nucleus. Okay, and a lot of people said, hey, you know what? That's a good idea. That seems to make a lot of sense. But shortly after his model came out, another scientist who was doing studies on like fluorescence and on how plants use chlorophyll, he discovered that electrons don't stay fixed distances from the nucleus. They can actually jump away and then fall back, jump away and fall back. So their distance from the nucleus isn't fixed. It can actually change based on how much energy the atom has. Right? So the Bohr model is like, this is what the atom would look like if you took a picture of it and froze it in time. Okay? But what an atom is dynamic. It's always moving. It's never stationary. So the electron cloud model is now the model we accept. And the electron cloud model supports that electrons can move around in this cloud to different levels and different energies. Okay? Now, the reason that de Broglie, and it is de Broglie who came up with the electron cloud model, okay, discovered this was he discovered that when you shot light at certain materials and then put them in the dark, they continued to glow. Okay? If something glows, it's giving off energy. And so his experiments led him to the findings that the reason it's glowing is because its electrons picked up energy from the light and they moved away from the nucleus. When the light source was removed, the energy that moved them away was gone. So they started falling back towards the nucleus. And as they fell back, they gave off the energy they had absorbed. They glow. for a short period of time. As they fall back, the material glows. Okay, plants use the same thing. Okay, chlorophyll works the same way. As the plant's chlorophyll absorbs energy from the sun, the electrons on the chlorophyll molecule get excited and they move away. Okay, and as they fall back down, the energy they give off is used by the plant to make sugar. Okay, so it's a similar process there. Right, but that's the model that we currently accept because it supports this idea that electrons do in fact move closer to or further away from the nucleus. Okay. All right. Questions there? All right. So the people that are probably the most important for you to know, Dalton. Okay, because Dalton came up with the original atomic theory. So Dalton and his 4 points. Okay, definitely important. Rutherford, definitely important because he discovered the nucleus. And de Broglie. Okay? De Broglie is important because he's the one who came up with the model we currently accept. And that's the electron cloud model. Okay, so back to this whole idea that atoms are indivisible. Okay, can I split an atom? Like me, no, I can't. I don't have the equipment. But is it possible to split one? Yeah, certain atoms anyway are easier to split than others. Okay, but it requires a lot of specialized equipment. So even though we know that atoms for the most part are indivisible, that is, they don't break kind of on their own. Okay, we do know that now they are divisible because we use nuclear power all the time. Nuclear fission is the division of atoms. Okay, now here's how that happens. In a nuclear reactor, there's like a particle gun. Okay, shoots like neutrons and stuff. Okay, and then there's these fuel rods. Okay, and on a fuel rod are pellets. Okay, and those pellets contain enriched uranium. When the neutrons hit those uranium pellets, the uranium atoms are very big and they're very unstable. So when they get struck, they break. Okay, and when they break, the pieces of them go off and hit other nearby uranium atoms and break them. And you get this chain reaction that releases a lot of energy. Okay, that's where nuclear fission energy comes from. Okay, if I've got a nuclear reactor and I want to generate a lot of electricity, I expose more of the fuel rod to the particles. Okay, and more of the nuclear reaction will occur. If I want to cool it off, I don't want as much power, then I pull the fuel rod out a little bit further so less of it is exposed. Okay? What happened at Chernobyl was they couldn't get the rod out and it was stuck in that position. All the water that was cooling it and whatever evaporated, and then they got this meltdown, which was like a runaway reaction they couldn't stop. Okay? The other kind of runaway reaction that you can't stop is a nuclear bomb. I'm going to teach you how to make a nuclear bomb. I can teach you that because it's very simple, but you can't get the materials. Okay? So in a nuclear bomb, or at least a primitive one, you have a bomb casing that's made of high explosive, okay? C4, plastique, okay, something like that. And in the middle is a big lump of nuclear material, plutonium, uranium, okay, something like that. Okay? When you set off a nuclear bomb, there's actually two explosions. A very small one, that's this high explosive blowing up, and then this one. The fission reaction that happens when the high explosive detonates, a whole bunch of particles immediately rush rapidly in towards this big lump of plutonium or nuclear material. And when they hit it, they start breaking its own atoms. And then its atoms, as they break, hit other atoms. And you get this chain reaction that just runs away, and you get the giant mushroom cloud and lots of destruction. All right? So it's actually, it means more technical than that. But at a very simple level, that's how a nuclear bomb works. It splits the atom, okay, by essentially shooting particles at it. Now, uranium atoms, for atoms, are huge. Okay? They're very, very big. And the bigger an atom gets, the less stable it becomes. right? Small atoms are very stable. We wouldn't try this kind of thing with like a lithium atom because it's a really small target. Okay? It's a much smaller atom. It's quite stable, doesn't want to break. It wouldn't yield a lot of energy even if it did break. Bigger atoms release more energy when they break. Okay? Everybody all right with that idea? All right, so the structure of the atom as we currently understand it is that there's a dense, positively charged nucleus where the neutrons and the protons reside, and then there's a large volume of space surrounding the nucleus in which we find the electrons. That's the electron cloud, and there's various energy levels within the cloud that we call orbitals. Okay, and where you find an electron is based on how much energy it has. So, in reality, an atom is made up of a lot of empty space, and that's what Rutherfords experiment proved. Those particles could get through and not hit any atoms because there was actually enough space in between them for them to go. Okay. All right, so all atoms are made of the same things, protons, neutrons, and electrons. What makes them different is how many protons, basically just protons, but protons, neutrons, and electrons they have. All right, so carbon atoms have 6 protons, while lead atoms have 82. Right? Their atoms are considerably different. This is also why lead's very heavy and carbon's very light. Okay, like graphite is carbon, okay? Basically pure carbon. Right? It's a very lightweight but quite strong material. Diamonds are also pure carbon. They're quite light but very strong. Okay, whereas lead is a very heavy, soft metal. Right? Its atoms are bigger. Okay, everybody kind of follow me there. Yeah, so it's the different numbers of protons that give the different materials their properties. Okay, looking at where the electrons might reside, okay, it's something like this. There's different orbitals or different places where you might find electrons. The most common place would be in this first orbital. That's the lowest energy orbital where electrons can be. Okay, the further away they get or the more extreme their shapes become, those are the higher energy orbitals. They can get to there, but if they don't keep that energy, they'll fall back lower down and they'll release it back. Okay. All right. These questions are in your workbook package, but you can just use them from here. Okay, I'd like you guys to answer. Let's say we probably have time to do like the first 4 here. Okay, so you don't have to write the questions down. They're in your workbook. Okay, so you don't need to write them down, but I'd like some complete sentence answers for the first 4, at least to finish class off today. Okay, we'll look at the others tomorrow.